Welcome, everyone. Thank you for staying around for this very last session of Strata. My name is Fangjin, and this is my colleague sitting over here, Gian. Both Gian and I are software engineers at Metamarkets. Metamarkets is a startup that's based in San Francisco, and today we wanted to talk to you guys about this idea of how to build out a real-time analytics data stack from existing open source technologies. So this talk is really based on our own experiences over the last few years with building out such a stack. And what we're going to cover is the problem that we were initially trying to solve, how we iteratively added pieces to the stack to be able to solve that problem, what the ultimate architecture of the stack looks like, and how you can download the stack at home and try it out for yourself. So the main problem that we were trying to solve, well, over the last few years, we've seen an explosive growth in social media. We've seen mobile applications that have been built for virtually every known purpose. And we've seen like the vast proliferation of mobile technology. And what all this technology has led to is that people and organizations and systems are now more interconnected than ever. So virtually every transaction that you do online nowadays has some sort of record associated with it. And even if you are a moderately sized company, you are probably generating a ton of event-based data. Contained within this data is a lot of useful insights. So for companies that can store and understand and analyze this data, there's a lot of useful things that they can do with it. At Metamarkets, we specialize in dealing with event-based data, and we are a data analytics company that's primarily focused in the online advertising space. So the product that we deliver to customers is an interactive dashboard where basically you can arbitrarily and interactively explore your data. So you can click around, you get an idea of different trends in your data. And in order to build this dashboard, there were several main challenges that we had to solve. One, we had to solve this general problem of how do you do data exploration. Another problem is data freshness. You know, how do you alert on events that are occurring right now? How do you explore on events as they're happening? And finally, because we are a software as a service company, we have problems that we have to solve around high availability. So as an engineer, anytime you're faced with a problem where you have to do analytics on top of very large data sets, the first technology that typically comes up is Hadoop, right? I have a lot of data. Why don't I just load it onto Hadoop, and then I'll query it, I'll get my insights, done. I can just go home, problem solved. Unfortunately, the simple solution, the naive solution, has a lot of drawbacks. MapReduce is amazing. MapReduce can handle virtually every distributed computing problem that you can think of. But because MapReduce is like this amazing general framework, it's not particularly optimized to do a lot of things very well. And in particular, MapReduce and Hadoop, they don't really make a lot of guarantees around query latency. So what we realized early on, and what I'm sure many of you in the audience realize as well, is that if you want fast queries on top of your data, typically you need to introduce this notion of a query layer. So while it is possible to build an entire backend system using only Hadoop, if you want to issue queries and have answers return in a reasonable amount of time, oftentimes you have to introduce this notion of a query engine on top of your storage. So the query engine that you should select and the query engine that we chose to select was really based on the types of queries that we were trying to optimize for. So the types of queries that we typically issue are arbitrarily filtered queries over event-based data. And what we care about is aggregates over certain metrics. So for example, within this class of queries, you can be asking questions like, how much revenue did I make over a quarter broken down by some demographic? Or in the online advertising world, who are my top publishers based on clicks over some span of time? Or we could be asking questions like, how many unique visitors did I see broken down by some dimension? So in these types of queries, what we're doing is we're not dumping an entire data set. What we're doing is we're looking at some filtered view of a total data set. And similarly, because we often deal with billions, if not trillions of events, we don't really care about any individual event. There's so many of them that a single one isn't particularly concerning to us. What we care about more is cumulative sums and aggregates and totals for spans of time. Now, by understanding the types of queries that we're trying to optimize for, we can begin evaluating what type of query engine should we choose. And this is actually a process that Metamarkets underwent early in its life. So the first query engine that we looked at was relational database management systems. And hopefully a lot of people out there are familiar with relational databases. Within this class, you have your MySQLs, you have your Postgres's, and you have many others. We experimented with Postgres, and what we found was the scan rates across our data using Postgres were a little bit too slow to power an interactive dashboard experience. So next, what we ended up trying was to use NoSQL key value stores. And within this class of data stores, you have your HBase, you have your Cassandra, and many others. And we actually experimented pretty heavily with using HBase to power our dashboard. And how we used HBase was basically we pre-computed out every possible query that a user could make. And we took all that data and we just dumped it into HBase. And what we quickly found with using a NoSQL key value store was the cost of pre-computation was getting to be a little bit expensive. And also, the time required to pre-compute out results was getting to be a little bit long. So next, we kind of looked at different commercial vendors that were out there, and there are many, I think, different commercial vendors. There's your so-called in-memory offerings. You have like MemSQL, you have SAP HANA, you have many others. And you have solutions from Amazon's Redshift or HP's Vertica. And when we were looking at commercial options for our query layer, we realized that at the time we were a pretty poor startup, and we couldn't really afford a lot of the offerings that were available. So instead, what we decided to do was we built our own data store, and that data store is called Druid. The Druid project was started around early to mid 2011, and we open sourced it in October of 2012. Since then, there's been a small but growing community. We have about 30 contributors right now from a couple of different companies. And Druid is built from the ground up to solve these problems around low latency data ingestion and also low latency aggregation. So Druid is highly optimized for the types of queries that we wanted to do. In the very first version of Druid, it was pretty straightforward to use. We basically had data, batches of data that were sitting around somewhere, and we would run MapReduce over this data, and we would index this data by partitioning the data into immutable blocks. And these blocks would then get loaded onto a set of Druid nodes known as historical nodes. On the query side of things, queries would go to these other types of nodes known as broker nodes. And broker nodes would kind of know what pieces of data live where. So in the very first implementation of Druid, we had a very simple, straightforward shared nothing architecture where we would load data through Hadoop. Actually all of the data that was loaded into Druid in the early days was immutable. And one cool thing about using immutable data is you basically get reconsistency for free. And through that, we got some pretty good read throughput. So why Druid is particularly good at doing aggregates and why it's particularly fast at scanning data is really a matter of the format in which Druid stores data and also the indexes that we build to help with the data that we have to scan. So I have a pretty simple data set example there. There's basically a timestamp column and a couple of other columns and metrics. Druid fundamentally is a column store. So each column in our data set is stored separately. If we examine the page column in the example I have up, what we can do with the values in the page column is we can basically map each value to an integer ID. So for example, this page column has two values, Justin Bieber and Kesha. Justin Bieber gets mapped to a value of 0, and Kesha gets mapped to a value of 1. So how we end up storing the page column is basically we store integer representations. So we store this array of zeros and ones. And similarly, for the language column, we have a single value that's English. And English can get mapped to an ID of 0. And for the language column, we can only store this array of zeros. So this method of mapping dimension values to integer IDs is known as dictionary encoding. And when you're storing an array of integers, you can get some pretty good compression. And you end up saving a lot of storage space. Another kind of cool thing that we do in Druid is we build bitmap indexes to help narrow down on the data we actually have to scan for a given query. So in this example that I have here, you can see that Justin Bieber, this value appears in the first 3 rows of our data. So we can create this representation, a binary array, which indicates in what rows a particular value is seen. So in this example here, Justin Bieber has some binary array associated with it where the first 3 values are marked as true. And similarly, the other value, Kesha, here has a binary associated with the last 3 values marked as true, indicating which rows these values appear. Now, if we want to issue a query that says, return me only that data filtered for rows that contain this value Justin Bieber, then we can simply look at the binary array that's associated with the value, and we immediately get which rows we have to scan. And we can do the same thing for Kesha as well. So if we wanted to know which rows contain Justin Bieber or Kesha, then we can look at the binary arrays associated with one value or the other, and simply do a Boolean OR operation of them together, and we get the final set of rows that we have to scan. So if you're familiar with search engines at all, this method is known as building an inverted index. And the cool thing about inverted indexes is when you have arrays of zeros and ones, they can compress really easily. So when we deployed Druid into production, we were pretty happy with the results. Druid gave us the ability to do arbitrary data exploration, and it also gave us the ability to do very fast queries. So Druid was highly optimized for the types of queries that we were trying to solve. Now, in the very first version of Druid, we still had some other problems. The only way that we could load data into Druid was to run these pretty long Hadoop jobs and batch load data into Druid. And we want to do things like we want to be able to alert on data that as it was happening. We want to use Druid to monitor our own internal operations. And all these use cases require this notion of real time. So we needed a way to be able to load data into our query layer in real time. And with that, I'm actually going to hand things off to Gian here, who's going to talk a little bit more about the data ingestion problem.
Hey, thanks, Fangjin. So I'm Gian Merlino. I'm another one of the backend engineers at Metamarkets. And Fangjin mostly works on the database, and I mostly work on the data pipelines. I'm going to walk you through how we built a faster data pipeline. Like Fangjin said, what we started off with at Metamarkets was a data pipeline that went essentially from data stored in Hadoop to data loaded into Druid. This is great. Queries are really fast, but it takes time to load data in. This is a problem. Users become accustomed to fast queries, and they become frustrated working with stale data. We also want to cover operational needs as well as historical analysis. Our product at the time was very good for historical analysis, very good for reporting, not very good for operational needs that had to work on data from the same day or even the same hour or the same minute. So why is this difficult? There's two obstacles essentially to a fast data pipeline. The first one is that we have to load raw data into Hadoop. This may sound trivial, but it's actually very important. Data needs to get into the system as fast as possible. The second issue is once the data is loaded into the system, we have to essentially materialize views into a query engine. That's basically what the Druid indexing process is. Looking at the data that's in Hadoop and loading it into a query engine that can then query it quickly. So let's tackle these one at a time, and hopefully when we've done both, we've solved the problem. The first problem of event delivery, we are tackling that with Kafka. If you're not familiar with it, Apache Kafka is a product that came out of LinkedIn. It's essentially a high throughput event delivery system. It's got a very straightforward, reliable design. There's a set of brokers that buffer incoming data and give consumers time to process it, fully decoupling the production and consumption of data. The architecture looks something like this. Producers on one side, consumers on the other side, and brokers sitting in the middle, making sure that the producers and consumers don't need to worry about each other. This sort of system is events come in one at a time, they can be consumed one at a time, and it sort of solves the fast delivery problem. There's no need to buffer things up and load it into HDFS in batches. We can see them as soon as they're there. So once we have this, the natural thing to do is to hook up Druid as a Kafka consumer, which is what we did. And the way we did that is we sort of looked at what we have with Druid. We have a query system, we have an indexing system. Why don't we just combine them together? And that's basically what we did. We now have an indexer that serves queries while it's building indexes. The architecture looks sort of like this. It's a little bit more complicated, but not too bad, I hope. Kafka brokers have data coming in real time. That data goes immediately to Druid real-time workers. Those are acting as Kafka consumers. They're building the data segments that Fangjin was talking about earlier, and as they're building them, they're also accepting queries from the Druid query broker. As they get those queries, they can answer them in one thread while they're building segments in another thread. This process is difficult to really optimize for. As you may imagine, the data structures required for fast updates are different from the data structures required for fast reads. So what we do is periodically, the Druid real-time workers essentially finalize a data segment they're working on, convert it into a fully read-optimized form that's now difficult to write to. It's immutable, but that's okay. We hand it off to the Druid historical cluster, which at day one of Druid was all we had. And it's that thing that's really great at handling large amounts of immutable data. And all the while, the query broker is farming out queries for the past hour or two of data to the real-time workers and all other time ranges to the historical cluster. Well, so we solved the delivery problem and we solved the loading problem. Are we done? Well, maybe. For simple use cases, yes. We can load events in real time and they're available for analysis immediately, but there are limitations. This data pipeline can't deduplicate events. That's a common problem in real-time pipelines. We can't join multiple event streams because we're essentially shoveling events directly into Druid indexes. There's no ability to do anything like that. We can't do any non-trivial pre-processing. These are all issues that we had at Metamarkets with the first version of our real-time pipeline. And we addressed them with Storm. Storm, if you're not familiar with it, is a stream processing system developed at a little company called Backtype, which was then acquired by Twitter and sort of popularized there. It processes one event at a time. You set up these things called storm topologies, which are essentially data comes in somewhere and then shuffles around a bit and then exits at some point. And so at Metamarkets, we have storm topologies that read data from Kafka, do some kind of processing, and then push data into Druid. What kind of processing do they do? Well, I mean, whatever is necessary. At Metamarkets, it's usually ETL type work. And the way that we approach building these storm topologies is first looking at our Hadoop jobs. In general, you sort of have a Hadoop job to start with. Maybe you wrote it in Pig, maybe you wrote it in Cascading, but you have something. And we translate that to a streaming system. Hadoop jobs do essentially three things. They load data, they map it, and they reduce it. Load and map operations are trivial to translate into a streaming system because they are one event at a time. Reduce operations can be windowed, and so reduce operation may be an aggregate or a group or a join or something like that. And what you do is you say something like, well, if you want to join two streams, you can buffer up tuples from one stream for 10 minutes and another stream for 10 minutes. Anything that comes in the same 10-minute window can be joined together. Anything that's more than 10 minutes apart, well, tough. And that tends to work for many kinds of problems. It's up to you to select those tuning constants that make sense for your data, but there's usually something you can do. The architecture looks like this. Events are still coming into Kafka, but now instead of going directly into Druid real time, we have Storm sitting between Kafka and Druid, doing all of that pre-processing stuff. And going back to the picture we've been drawing, this is the story so far. We first had just Hadoop, great for storage, very slow for queries. Fix that by adding a query layer. In our case, it's Druid. Hadoop is still great for storage, but not great at loading into data into Druid very quickly. So we replaced that with Kafka and Storm. And this is what we bought. Druid queries can reflect new events within seconds. That's great. The systems are fully decoupled. If there's an issue with Storm, it does not affect queries, nor does it affect ability to take events in at Kafka, which is very important because it means that events at our customers don't need to be buffered up. They can always deliver stuff to Kafka, and if an issue is occurring with our processing pipeline, there's no problem. It also means issues in the processing pipeline don't affect queries. There's no query downtime, no delivery bus downtime. There are brief delays in processing during maintenance, and that's just sort of because of how Storm works. When you do a Storm code push, you restart the topology, it takes a couple minutes to start back up. It's not perfect though. We gave some things up. Stream processing is not the solution to all problems. It's difficult to handle corrections of existing data. You can imagine that if you have a stream processing system where data is coming in, being loaded into real-time Druid, and then after, let's say, 2 hours being finalized and shipped off to the historical cluster, what do we do if an event comes in 3 hours late? Well, in a streaming-only system, you have no choice but to drop it on the ground, which is not always the best thing to do. Also, if you're joining two streams, maybe you find out that 99% of your data comes in within 10 minutes, but that last 1% can take a day to come in, and you don't want to hold a day of data in memory. Hadoop was actually really good at doing these kinds of things. So we can address these problems by bringing back Hadoop. We essentially run a streaming system on all the data that is sort of on time, and that data is coming in through Kafka, going through Storm, being loaded into real-time Druid, and finalized and shipped off to the historical cluster. But then, for anything that pipeline misses, or for any ETL pipelines where we need a large join window, Hadoop can come in later, can come in hours later, days later, whatever you want, and reprocess the data and regenerate immutable segments and then replace them in Druid. This is actually something that Druid makes really easy to do. Druid is very good at doing atomic updates of these immutable segments, and the query broker makes it so you don't have to worry about that whole process. You don't have to worry about when segments are being updated, when they're being handed off. You make queries to the query broker, and you don't really know the difference, which is great. So at this point, the stack was kind of like this. We had to sort of move out the other pieces because they got a little bit too complicated. But events are coming into Kafka, and then in real time, on-time data is being processed by Storm and real-time Druid. And some hours later, all data is being processed by Hadoop and then being loaded into the historical cluster in Druid. And this gets all those nice benefits that we were talking about earlier. We get the fast queries on fresh data of the real-time system, and then we also get the guaranteed correctness, eventually, of the batch system. So earlier we promised that we'd talk about trying this stack out at home, and now's the time for that. The cornerstones of the stack are all open source. Storm is an Apache incubator project. Hadoop and Kafka are also Apache projects. Druid was open sourced by Metamarkets in 2012. These are the websites. I think the slides are going to be online if you want to download it later. There's also the little arrows. Don't forget them. They can be the hardest part of setting up a stack. Luckily, in this case, all 4 little red arrows have something. From Kafka to Storm, there's a extension in Storm Contrib called Storm Kafka. From Kafka to Hadoop, there's another project from LinkedIn called Camus. It essentially just dumps data from Kafka to Hadoop on a schedule that you define. From Hadoop to Druid, that's actually built into Druid. There's a thing called the Hadoop Druid indexer. That's the very first data loading system we developed for Druid. And then from Storm to Druid, there's something called Tranquility, which we open sourced like an hour ago. Tranquility is used in production of Metamarkets. It has one job: push data into Druid in real time. It manages partitioning, redundancy, and schema changes seamlessly for you. You sort of set up the configuration and then send data through this very simple API that can be used with any JVM language. We've bundled Storm and Finagle bindings with it because that's what we use internally, but you can use it with whatever you want to use it with. Open source this week, and this is the GitHub URL. So yeah, to sort of tie things up, this is something that we call the real-time analytics data stack, mostly because it stood for RAD stack and we needed a name. You can use it to answer queries quickly on fresh data. Kafka provides fast, reliable event transport. Storm and Hadoop are used for the ETL. They clean and prepare data for Druid. And Druid handles all queries and manages complexity in the serving layer, doing that really nice job of making sure that you don't have to worry about things over there. Thank you. If you have questions for either me or Fangjin, yeah, what's up? So the question was, how exactly is the decoupling done in Kafka between producer and consumer? Kafka stores data on disk. It's sort of an append-only format on disk. There's these log segments where data is just written to sequentially, and they're evicted after some amount of time. I believe a typical Kafka configuration will make that time days, such that they can be decoupled by about that long. And if your consumers are down for more than your retention period in Kafka, they will lose data. Right. So what kind of range queries are you talking about? Like time range or like okay, so the question was how do we handle range queries? Druid treats time very specially, so I'll answer that first. Druid essentially always, so it's a shared nothing architecture, and like all shared nothing architectures, it partitions somehow. Druid always does the first partitioning on time, and so time range queries sort of naturally fall out of that. And the reason for that design was just because of the observation that the vast majority of queries, at least in our use cases, had time ranges in them. So from the very get-go, if you have a time range in your query, you can cut off all data that is not in that time range. And there's a storage granularity in Druid where you that's the granularity of that index, and most people use either hour or day in the community and also internally at Metamarkets. Within a time range, there's typically, if you have a large enough data set, a secondary shard on something, and a good thing to pick that secondary shard on is some column that has a lot of values in it.
Between Kafka, Clara, and Druid, how do you monitor,
So the question was monitoring and how do we make sure that things are making their way through the pipeline. That's a great question. We just spent a while working on that. What we do is we have an in-house metric system that's actually built on Druid. So we have our production Druid cluster that has our customers' data, and then we have a secondary metrics cluster that has our internal metrics, and we feed metrics of all stages of the data pipeline into that secondary cluster, and then sort of look at that to make sure things are making their way through, and our alerting is set up there. Anything else to say?
Yeah, so I have one comment to add onto that. So Druid comes out of the box with a set of metrics that it periodically emits. And these metrics may be like system level metrics like CPU, JVM. We also have like internal metrics for the system itself. Like they're very Druid specific metrics. And from that, in our internal metrics cluster, we can get a really clear idea of what exactly is happening in our cluster. So we've kind of repeated the same thing for the other pieces of our stack as well.
the client API to the query.
Do you want to do this?
Yeah. So Druid has its own native API for queries. Right now, it responds to queries over HTTP post requests. So there are basically JSON objects, JSON blobs that you build, and they contain various query parameters. People have built other ways to query Druid because writing JSON blobs by hand is extremely painful. So we have an R adapter, if you're familiar with the statistical language R. We have a Python adapter where you can query Druid using a pretty simple setup using Python. And we also have a SQL adapter as well. Druid doesn't support full SQL, but it does support some queries that can be mapped into SQL queries. So we have an adapter there as well.
Cool. Call it?
Yeah, all right. Thank you, everyone.